So here I have my Simulink model external mode raw sensor check running. You'll see that I have a MiniQ line sensor block right here. Each of the displays over here on the right side represents one of the sensors at the bottom of the MiniQ robot, and there are five separate sensors, therefore five displays, as well as we have a display down here for the line value, but for our immediate purposes, let's take a look at display 2. So right now I have the MiniQ robot running over a white surface, and as I gradually move the MiniQ robot over a black line, what you'll see is that there's a significant jump downwards in display 2, and that's with the MiniQ robot being over a black line. And as I move it off, you'll see that the value raises to a significantly high point, about 973. So we're going to want to figure out what that threshold jump is. When does that big drop happen? Because for our next program where we're trying to get the MiniQ robot to stay within a box, in order to signal that it's hit a black line, we need to have that sensor 2 value register the black line. Therefore, the jump probably happens around 900. So we can say that when display 2 lowers under 900, it is likely that the MiniQ robot is about to hit a black line, therefore do a separate set of movements. So this is the Simulink model stay in a box, and we've expanded on the sensor read model that we looked at previously by adding in a chart. And you can see that this chart is still on the same path as display 2. We've just moved it up here. By clicking into the chart, we can see that what it represents is a flow between states, forwards, backwards, and left, depending upon a line sensor value for display 2. And we can see that if the value is less than 900, it's going to pass from the forward state to the backward state, the direction of the arrow. It's quite obvious. Our model is always going to begin through an entry point, and that natural entry point is represented by an arrow with nothing connecting to the top of it, just a circle. You can see it right here going into forward. So that's our default state, and whenever you create one of these state flow models, a chart, you're going to want to include a default state, and that's how you do it. What we've done though, after when the MiniQ robot hits a black line and the value for that will be drops below 900, it'll go backwards for 0.5 seconds, and then it will go left for 0.5 seconds before returning back to its default state. So here for the backwards and left states right here I've highlighted, that resembles the dead reckoning movements that we looked at a little bit earlier. We've just combined it now with a raw sensor value here to initiate the whole dead reckoning process of moving from backwards to left a given amount of time. So we can hit this upwards arrow at the top to return to our Simulink model, and the outputs R and L are fed into a MiniQ motor block, and ultimately what it's going to allow us to do is get our MiniQ robot to stay within the confines of a box outlined by black tape. So we can expand upon the stay in box model by, instead of using just one sensor that was previously just within display 2, we can use the two outermost sensors on the MiniQ robot to detect either the robot meeting a line on the right side or on the left side. And in order to include those most exterior sensors, we have to add variables within our chart. And what I've done is I've made some input values, sensor left represented by SL, and sensor right represented by SR. So the flow chart is a little bit different, state flow chart. The difference being that if the sensor right value falls under 500, it moves into a turn. If you zoom into the right sensor there. So it's a turn with negative 255 for the right motor and then positive 255 for the left, and it's vice versa if the left sensor meets the line. So there really are three conditions which can happen now. The original one where the front sensor, here it's registered as 300, but really previously it was 900. If that frontmost sensor meets the line, what's going to happen is it's going to go backwards and then left. But if the exterior sensors meet a line, what's going to happen is just a turn into the line or outside away from it. So experiment with some of these variables. It's a little bit more advanced than just the simple stay in the box model, but I think that you can produce some pretty interesting behaviors just by changing some of the sensor values and especially the turn values within each state. So let's go back to our original model and let's run it. So let's start thinking about line following. Before we had our MiniQ robot just bounce within a square. What if we have it just bounce in and out off of a line? And in this model that I'm going to show you, this Simulink model, I'm going to talk about two sensor line following, and that is using the two outermost sensors on the MiniQ robot, and there are 5 sensors facing downwards on the bot. The values and the readings from those are going to be fed into our chart right here. So I'm going to double click in. Now you'll notice that the values are being assigned the variable label as LS and RS. We go into our state flow chart by clicking into it, and LS and RS are what cause the transitions between the different states: forwards, left pivot, right pivot. And these are the reflected light intensity values for each of the sensors. And if you've calibrated your MiniQ robot by doing the external mode sensor check, as we did at the beginning of the video, you'll know exactly what these outermost sensors should read. But in my case, my example, the threshold value for example, going from the forward state to the right pivot state is the left sensor being less than 500, and then immediately jumps back to the forward motion. So we can go ahead and we can deploy this to our hardware by pressing the button up in the top right, and from there we should see a relatively smooth pattern for our robot following a line. Here's the Simulink model, which represents a different kind of line following. The title for the model is Bang Bang Line Following, and then that's exactly the way we can describe the line following behavior of our MiniQ robot once we've deployed this to our hardware by pressing this button up here in the top right. It says deploy hardware. But before we explore a little bit more, let's take a look at where we are getting our values from our chart. Well, going into our chart. First of all, the raw values are attached to a terminator, therefore we're not getting any readings from them that we're going to use within our model. Where we are getting some values is the line value reading here. And what the line value means is that at any given moment, the line can be under one of the 5 MiniQ sensors, and those are numbered from 1 to 5. So let's say, for example, a line is under sensor 4, so the output value would be about 4, and as it transitions over slightly to a third sensor, which is in the middle, you'd see that that value, the line value, would shift to a 3. So let's click into the chart and let's take a look at this. So we have our entry point up here going into our first state, which is forward, and both R and L are assigned values of 255. Positive direction meaning the robot's going to go forward, and we have 2 states you could possibly go, right and left. And you'll notice that if we compare the values on this left side to the ones relative on the right, the median point for those is 3.0, because here on the leftmost side it's 2.90, over here is 3.10. So really what I'm trying to do is get the robot to stay over sensor 3 as often as possible. So if the line value moves away from 3 in the negative direction, value is, or actually positive direction, value is bigger than 2.90, it's going to go forward. But if it's less than that, it's going to move into a left state. So this is actually moving in the left direction because we want it to be over. The sensor value is 3, but it's moving below that, so it has to take a left turn to correct itself. And it is exactly the opposite on the other side, where the line value is increasing over what we want as 3.0, and the robot has to take a right turn to correct itself. So that's what we're trying to simulate right here, and what it causes the robot to do is almost bump into the line and off it in a kind of way that it's slamming itself against the line. banging against the line. So let's deploy this model to hardware and see what results. So here we have our third form of line following, and perhaps the most precise and smooth manner of getting your MiniQ robot to follow a line smoothly. The Simulink file is called PID Line Following, and PID stands for Proportional Integral Derivative, and that is the mathematical calculation which checks how far, in our case, the robot has deviated from an intended behavior of being on a line, reads that data and makes a mathematical correction back to being on the line. So it's very precise. It's taking in feedback from the sensors and doing a mathematical calculation. And you can click into this PID controller to check out exactly what that calculation looks like. It's no joke, but we're not going to talk about that here. What we're wanting to look at is the general flow of things from the line sensor going into a set point, which is our intended behavior for our robot, is to stick over sensor 3, and then it passes through the PID controller to figure out what type of correction needs to happen. And in here we have some formulas to talk about motor speed, because part of the correction towards the intended behavior involves fluctuations in speed, because it's all about getting our robot to follow a line as smoothly as possible. So there are no charts in here, just a variety of things that you can look into to help you better understand how this type of smooth line following is occurring. If you want it, you can try and experiment with some of the values up here, maybe this 25, maybe the set point, to see how that affects the line following. But in general, this is a very nice model to see our MiniQ robot follow a line as it should, smoothly, precisely, and with vigor. So let's say we want to make our proportional line follower a little bit more complex. Let's say, for example, it's line following and an object falls in its way on the path, and we need our robot to stop there. We don't want it to crash in the object, but just take a little pause. So we have the basics of the line following model we looked at previously. The main addition has been this chart. Now, the chart also includes the IR sensor block, the MiniQ IR sensor block, because we need some type of proximity reading for the front of the MiniQ robot and what could potentially be there. And so that's being fed into our chart. And if we double click into the chart, you'll see that I've just named the states go and stop. And within go, I have if v will equal fast, if that's a state which the robot enters into, and there is no condition which would cause it to move into the stop state. That condition would be if the prox reading is bigger than 10. And I can tell you right now that what the IR sensor was attached to is right here, prox. So you can see that that's the variable which is taking in the numerical values the sensor's throwing at it. If that value is bigger than 10, the robot's going to move to a v equals slow. Otherwise, it's going to go fast. Now, what is slow and what is fast? So if we go back, you can see that we do have one value of a constant as 15 for the fast motor speed. You can see if you zoom in, it's fast. And we have -5 as the slow motor speed. And we know from previous experimentation with the MiniQ that a negative value means the robot's actually reversing, or that wheel is reversing. And the way I figured out how to create this model is that the robot doesn't actually stop like you would at a red light, but it backs up and hovers from an object. That's the best way I could replicate this type of line following objective we have of it stopping when it meets an object, is it really just backs off it and heads towards it again. But it does suffice to achieve our objective, which is ultimately to have an obstacle avoiding robot with a line following behavior. So this model can still be improved, but as is, you can see what I mean, and you can see how the chart and the different speeds being fed to the motor can affect the MiniQ.